Okay, so what we're going to do here is I'm going to do the first tree together, state without proving a result that connecting the degrees of the vertex of a graph G with the number of edges, okay, the number of its edges. Use this result to find the number of edges of a tree-regular graph with 10 vertices and explain why it is not possible to construct a three-regular graph with 9 vertices. Well, let's just have a quick look at an example. What I'm going to do is actually just to sort of switch over to pen and paper here for a second. So let's just actually draw a very simple graph like this, okay? And what we can see very quickly, oops, is that we have 3 vertices, okay? And we have 3 edges. Okay. Now, but it's actually not. We're actually asked what in the terms of the degrees of each edge. So we have 2 here, 2 here, and 2 here. That's the degree of each vertex. That is the degree of each of the vertices there. So essentially, what we're going to do here is we are going to sum of the degree sequence. Okay. The sum of the degree sequence equals 2 times number of edges. Now, state without proving, okay? But let's just actually just sort of cross-check that against another example. So let's go for 4 vertices this time, okay? So 4 vertices, the degree of each vertex is 2. Okay, 2 times 4 is 8. Okay. The 2 times 4 is essentially 2 plus 2 plus 2 plus 2. That is the sum of the degree sequence. And also that we have 4 edges there. 1, 2, 3, 4. That seems to check out. Let's just go one step further. Add in 2 more edges. Okay. So we actually have 6 edges. But what does that make our degree sequence? 3, 3, 3, 3. Add all of those up. 3 plus 3 plus 3 plus 3, that is 12. We have 6 edges. 2 times 6 is, yeah, everything seems to check out. So how many edges? So what we're asked for was a tree-regular graph with 10 vertices. Okay. So, oops, a little bit rocky there. So that is the number of edges is simply 3 by 10, which is 30, divided by 2. Okay, so that is 15 edges. Okay, that's the sum of the degree sequence divided by 2, which is another way of expressing what we had there previously. Okay, so 3 regular graph with 9 vertices. Okay, so the sum of the degree sequence would be 27. Okay, but that means the sum of the degree sequence being 27, that means that you would have 13.5 edges. That does not make sense. Can't happen. Okay, the reason it can't happen, can't have 13.5 edges. Okay, so that's that. So let's go back to our question sheet. Okay, so a simple connected graph has 7 vertices, all having the same degree d, so it's d regular. State the possible values of d, and for each value also give the number of edges in the corresponding graph. So it is just important to remark that it's a simple connected graph, okay? So it means that we have to have at least degree 2, okay? Also, it's a simple degree connected graph, so we could the maximum is 6, okay? Because if we have if it's more than 6, then if there's 7, if it has degree 7, that means it has to connect to one vertex at least twice, okay, which we can't have. So essentially, to start off with, D is between 2 and 6, but which values between 2 and 6 are valid. So what I'm going to do, actually, just going to switch over to some pen and paper here. Okay, so very simply what I'm going to do very quickly is just demonstrate D is equal to 2. So there we have 5 vertices. Okay, so just make sure. I was nearly going to draw a hexagon there. Okay, so that's D is equal to 2. That works fine. Okay, now the number of, so we, N is the number of vertices, or actually I'll just go V for number of vertices actually. Okay, that's equal to 7. The degree sequence there, or the degree is for each vertex, it's k regular. D regular, it's 2. So the number of edges is V D divided by 2. In this case, that's 7. And you could probably count them out there yourself. Okay, so D equal to 3. Is that possible? So, well, in this case, E equals V D over 2. That is equal to 7 times 3 over 2. That is equal to 10.5, as in 21 over 2. No, not possible. Okay. So what about D is equal to 4? E equals VD over 2. That is 7 times 4 over 2. That's 14. And actually what I'm going to do is actually just draw it out up here. I'm just going to superimpose it on what I have done already. What I'm going to do here is sort of connect it like that. So nice little artistic shape there. Essentially, just actually my pattern is the vertex that connects is directly connected to your vertex by D2, and then what just comes after that, the neighbor after that, so to speak, your two nearest neighbors on either side. Perfect. Okay, so D is equal to 5. Is that possible? E equals VD over 2. That is 35 over 2. Pardon me if I speed on a bit. That is 17.5. No, not possible. Okay. D equal to 6. Let's just give ourselves some room there. Yes, that's completely possible. E equals VD over 2. That is 7 times 6 over 2. That is 21. Okay. And essentially, just to continue on what I've done there before, it's essentially just connect up everything else. It's a complete graph. So just connect everything that's not connected. Okay. There we go. Perfect. So I think I might have missed one there. I think I got them all there now. No, I don't. No, I think that's them all. Okay. So essentially, every vertex here should be connected to every other vertex. Now, so actually, right at now, what we have here is degree is equal to 6. Okay. What happens if I add in another degree? D equals 7. Essentially, it stops being a simple graph. So, for example, I might have to add in another edge here like that. That just breaks the rules of a simple graph. So essentially, D is equal to 6 is the stopping condition. Okay, so the answers are D is equal to 2. That's fine. We get 7 edges. D is not equal to 3. D is equal to 4. Yes, that's fine. We get 14 edges. And D is equal to 6. Yes, that's fine. We get 21 edges. Okay, I'm just going to pause it there and just check what is left. So another simple connected graph has 6 vertices, all having the same degree n. So draw such a graph when n is equal to 3 and state the other possible values of n. I'm going to be very brief at this one. So what I'm going to do is actually just do it very quickly. This is my 6 vertices there. Okay. So what I will do here is just to show what it looks like when n is equal to 3. I will just connect them all around the edge like that, a perimeter, so to speak. And then what I will do is just my own personal preference. I will connect vertices that are directly opposite to each other. Okay, that is D on 3 regular on 6 vertices. So the other possible outcomes are n is equal to 2, which is just what I started off with there before I added in these edges here. N is equal to 3. N could equal to 4. Yeah. And n could equal to 5. Okay. Essentially what happens here is just like I've done in the previous example, is that the n time without the number of edges times the degree, which this is the degree in each instance, actually always gives a positive or an even number. And when you divide that by 2, you get the number of edges, and it always works out to be an integer that makes sense. Okay, so that is it. I think I'll leave it there. We've done a lot of work.